The universe is a place of infinite wonder, stretching beyond the limits of our imagination. Yet it's also a realm filled with questions that defy even the brightest minds. Despite centuries of exploration and discovery, there are still mysteries lurking in the cosmos that leave scientists scratching their heads. From the strange behavior of black holes to the eerie silence of the universe, these enigmas challenge everything we think we know about space and time. Today, we're diving into 20 of the most mind-bending space mysteries that continue to baffle experts and ignite our curiosity. What makes these puzzles so compelling? Why do they captivate not just scientists, but anyone who gazes up at the night sky? And perhaps most intriguing of all, what secrets does the universe still hold from us? Let's embark on this journey together and uncover the cosmic riddles that keep us searching for answers. Imagine this: you're looking at a galaxy, its stars swirling in a cosmic dance held together by gravity. But here's the catch: what you're seeing, all those stars and gas clouds, only accounts for a tiny fraction of what's actually there. The rest, it's invisible. Completely undetectable, yet it's there, tugging at the fabric of space, shaping the universe as we know it. This is the mystery of dark matter. Dark matter makes up roughly 27% of the universe, yet it doesn't emit, absorb, or reflect light. It's like a ghost silently influencing everything around it. So how do we even know it exists? Scientists first noticed something strange when they observed galaxies spinning faster than they should. Based on the visible matter alone, these galaxies should have flown apart, but they didn't. Something unseen was holding them together, something with immense gravitational pull. That something is dark matter, but here's where it gets even more puzzling. Despite decades of research, we still don't know what dark matter actually is. Is it a particle, a new kind of physics we haven't discovered yet? Experiments deep underground and in space are hunting for answers, searching for even the faintest trace of these elusive particles. And the stakes couldn't be higher. Understanding dark matter isn't just about solving a cosmic riddle, it's about unlocking the secrets of the universe's very structure. Without it, galaxies, stars, and even planets might never have formed. And just when you think the universe couldn't get any stranger, there's another invisible force at play, one that's even more mysterious and far more powerful. But we'll get to that in a moment. For now, let's sit with this thought. Dark matter is out there, shaping the cosmos, and yet it remains one of the greatest unsolved mysteries in science. What could it be, and what would it mean if we finally found it? If dark matter is the universe's invisible scaffolding, then dark energy is the mysterious force pushing it apart at an ever-increasing speed. Picture this: the universe isn't just expanding, it's accelerating, and the reason, a force so baffling that scientists have named it dark energy. This enigmatic energy makes up a staggering 68% of the universe, dwarfing even dark matter. But what exactly is it, and why does it defy everything we thought we knew about physics? The story of dark energy begins in the late 1990s, when astronomers studying distant supernova made a shocking discovery. They expected the universe's expansion to be slowing down due to gravity, but instead they found it was speeding up. It was as if the cosmos had hit the gas pedal, and no one could explain why. Enter dark energy, a term coined to describe this mysterious force driving the acceleration. But here's the kicker: we have no idea what it actually is. One leading theory is the cosmological constant, an idea first proposed by Albert Einstein. He suggested that empty space itself might have an inherent energy, a kind of anti-gravity pushing things apart. But even Einstein later dismissed the idea as his greatest blunder. Now it's back in the spotlight as a possible explanation for dark energy. Another theory points to quantum vacuum energy, the idea that empty space isn't truly empty but filled with particles popping in and out of existence. Could this quantum froth be the source of dark energy? Maybe. but the math doesn't quite add up. The predicted energy is far too strong to match what we observe. So, what does this mean for our understanding of the universe? Dark energy isn't just a cosmic curiosity, it's reshaping our entire view of reality. If it continues to dominate, the universe could keep expanding faster and faster, eventually tearing galaxies, stars, and even atoms apart in a scenario cosmologists call the Big Rip. But for now, dark energy remains one of the greatest unsolved mysteries in science, a force that challenges our deepest theories and keeps us searching for answers. And speaking of the universe's expansion, there's another puzzle tied to this cosmic acceleration, one that takes us back to the very beginning of everything. But we'll get to that next. For now, let's sit with this thought. Dark energy is out there, shaping the fate of the universe, and yet it remains as elusive as ever. What could it be, and what would it mean if we finally unraveled its secrets? Now, let's turn our attention to a mystery that's shaking the very foundations of cosmology, the Hubble Tension. Imagine trying to measure the speed of a car, but every time you use a different tool, you get a completely different result. That's essentially what's happening with the universe's expansion rate. Scientists have two main ways to measure how fast the cosmos is growing, and they're giving us wildly different answers. This discrepancy is called the Hubble Tension, and it's causing a crisis in our understanding of the universe. So, how do we measure the universe's expansion? One method looks at the cosmic microwave background, the faint afterglow of the Big Bang. By studying this ancient light, scientists can calculate how fast the universe was expanding shortly after its birth and extrapolate that rate to today. The other method uses what's known as the cosmic distance ladder, which involves observing nearby stars, supernovae, and other objects to measure distances and velocities directly. Both methods are incredibly precise, but here's the catch: they don't agree. The cosmic microwave background suggests a slower expansion rate, while the cosmic distance ladder points to a faster one. The difference might sound small, but in the world of cosmology, it's a glaring inconsistency. What's causing this tension? Some scientists think it could be a sign of new physics, something beyond our current understanding of the universe. Maybe dark energy isn't constant but changes over time. Or perhaps there's an unknown particle or force influencing the cosmos. Others suggest it might be due to systematic errors in our measurements, though repeated experiments have yet to uncover any major flaws. Whatever the cause, resolving the Hubble tension is crucial. It's not just about getting the numbers to match, it's about understanding the fundamental nature of the universe itself. And this mystery takes us even deeper into the cosmos, back to the very beginning of everything. Because if the Hubble tension is pointing to new physics, it could reshape our understanding of the Big Bang and the early universe. But before we dive into that, let's pause and consider this. The universe is expanding, but we're not entirely sure how fast. What does that mean for our place in the cosmos? And what secrets might we uncover if we finally solve this cosmic puzzle? Now, let's rewind the cosmic clock all the way back to the very beginning, the Big Bang. It's the event that set the universe in motion, the moment everything we know, stars, galaxies, planets, even time itself, came into existence. But here's the thing, when we try to look at the exact moment of the Big Bang, our understanding of physics breaks down. This is the mystery of the Big Bang Singularity. Imagine trying to cram the entire universe into a single point, a point so infinitely small and dense that it defies all logic. That's what the Big Bang Singularity is, a moment where the laws of physics as we know them simply stop working. Gravity becomes infinitely strong, space and time lose all meaning, and our equations collapse into chaos. It's like trying to divide by zero. It just doesn't compute. So why is this such a big deal? Because the Big Bang Singularity isn't just a cosmic curiosity. It's the ultimate question mark at the heart of our universe's origin story. To understand it, we'd need a theory that unites the two pillars of modern physics: Einstein's theory of general relativity, which explains the large-scale structure of the universe, and quantum mechanics, which governs the behavior of the smallest particles. The problem: these two theories don't play well together. General relativity breaks down at the quantum level, and quantum mechanics doesn't account for gravity. This is where quantum gravity comes in, a theoretical framework that aims to bridge the gap. One leading candidate is string theory, which suggests that particles aren't tiny dots but vibrating strings, and that these strings could explain the fundamental forces of nature, including gravity. Another idea is loop quantum gravity, which proposes that space itself is made up of tiny, discrete loops. Both theories offer tantalizing possibilities, but neither has been proven yet. So, what does this mean for our understanding of the Big Bang? If we can crack the code of quantum gravity, we might finally glimpse what happened at that singular moment. Was the Big Bang truly the beginning of everything, or was it just one event in an endless cycle of universes? These are the questions that keep cosmologists up at night. And speaking of time, the Big Bang Singularity isn't just a mystery about the universe's birth, it's also a puzzle about the nature of time itself. Because if time began at the Big Bang, what came before it? Was there even a before? These questions take us into the realm of another mind-bending mystery, one that challenges our very understanding of time and space. But we'll get to that next. For now, let's sit with this thought. The Big Bang Singularity is the ultimate cosmic riddle, a moment where science meets the unknown. What secrets might it hold, and what would it mean if we finally unraveled them? Now, let's venture into the heart of one of the most perplexing puzzles in modern physics, the black hole information paradox. Imagine throwing a book into a fire. The pages burn, the ink fades, but in theory, if you could track every particle of smoke and ash, you could reconstruct the book. That's the principle of information conservation, a cornerstone of quantum mechanics. But what happens when you throw that book into a black hole? According to our current understanding, the information might be lost forever. And that's a problem, a big one. Black holes are cosmic vacuum cleaners, sucking in everything that crosses their event horizon, the point of no return. Once something falls in, it's gone, right? Well, not so fast. In the 1970s, Stephen Hawking made a groundbreaking discovery. Black holes aren't completely black. They emit radiation, now known as Hawking radiation, which causes them to slowly evaporate over time. This was a revolutionary idea, but it came with a catch. If a black hole evaporates completely, what happens to all the information about the stuff it swallowed? According to quantum mechanics, information can't be destroyed. But according to Hawking's calculations, it seems to vanish into thin air. This is the black hole information paradox, and it's been keeping physicists awake at night for decades. So, how do we resolve this paradox? One leading theory is the holographic principle, which suggests that all the information about what falls into a black hole isn't lost. It's encoded on the black hole's event horizon like a cosmic hard drive. Imagine the event horizon as a two-dimensional surface that stores all the information about the three-dimensional objects inside. It's a mind-bending idea, but it could solve the paradox by preserving information in a way that doesn't violate quantum mechanics. Another theory proposes that information might escape through Hawking radiation, encoded in subtle patterns that we haven't yet figured out how to decode. But here's the kicker: if information isn't lost, it means our understanding of black holes, and maybe even the universe itself, is incomplete. This paradox isn't just a theoretical curiosity, it's a fundamental challenge to the laws of physics as we know them. Resolving it could revolutionize our understanding of space, time, and reality itself. And speaking of black holes, there's another mystery lurking in their shadowy depths, one that's just as baffling and even more dramatic. But we'll get to that next. For now, let's sit with this thought. Black holes might be the ultimate cosmic enigmas, swallowing not just matter and light, but the very rules that govern our universe. What secrets do they hold, and what would it mean if we finally cracked the code? Now, let's zoom in on one of the most baffling cosmic puzzles, the origins of supermassive black holes. These behemoths, millions or even billions of times more massive than our Sun, sit at the centers of galaxies, including our own Milky Way. But here's the mystery: how did they get so big so fast? The universe was just a baby when these giants appeared, and their rapid growth defies everything we thought we knew about black hole formation. To understand why this is so puzzling, let's start with how black holes usually form. Most black holes are born from the collapse of massive stars. When a star runs out of fuel, it explodes in a supernova, and its core collapses under its own gravity, forming a black hole. But here's the catch: this process takes time, a lot of time, and yet supermassive black holes were already lurking in the early universe, just a few 100 million years after the Big Bang. That's like finding a skyscraper in the middle of a desert that's only been around for a week. How did they grow so quickly? One theory is direct collapse. Imagine a massive cloud of gas, so dense and unstable that it skips the star-forming stage entirely and collapses directly into a black hole. This could create a black hole with a head start, already thousands of times more massive than one formed from a single star. But even this theory has its limits. How did these gas clouds get so dense so early in the universe? And why haven't we seen direct collapse happening in the modern cosmos? Another idea points to primordial black holes. These are hypothetical black holes that could have formed in the chaotic moments after the Big Bang, when the universe was a seething soup of energy and matter. If these primordial black holes existed, they might have served as seeds for supermassive black holes, growing over time by devouring gas, stars, and even other black holes. But again, there's a problem. We've never detected a primordial black hole, and their existence remains purely theoretical. So, what does this mean for our understanding of the universe? Supermassive black holes aren't just cosmic oddities, they're central to the story of galaxy formation. Every galaxy we've observed seems to have one at its core, and their growth appears to be intertwined with the evolution of the galaxies themselves. Did supermassive black holes form first, pulling galaxies into existence around them? Or did galaxies form first, feeding their central black holes over time? It's a chicken and egg problem on a cosmic scale, and speaking of black holes, their behavior raises even more questions. For instance, how do they manage to grow so massive without blowing away the very material they're trying to consume? This takes us into the realm of another mystery, one that's just as perplexing and even more dramatic, but we'll get to that next. For now, let's sit with this thought. Supermassive black holes are cosmic giants that shouldn't exist, at least not as quickly as they did. What does their existence tell us about the early universe, and what secrets might they still be hiding? Now, let's shift our focus to a cosmic phenomenon that's as fleeting as it is powerful: fast radio bursts, or FRB. Imagine a burst of energy so intense that it outshines entire galaxies, but it lasts for just a fraction of a second. These mysterious signals, originating from deep space, have been baffling scientists since their discovery in 2007. What are they? Where do they come from? And could they be a sign of something even more extraordinary, like extraterrestrial intelligence? Fast radio bursts are exactly what they sound like: incredibly brief, incredibly powerful bursts of radio waves. They last just milliseconds, but in that tiny window, they release as much energy as the sun does in 80 years. The first FRB was detected by accident, a blip in the data that no one could explain. Since then, hundreds more have been recorded, each one a cosmic flash in the pan. But here's the catch: most of them are one-off events. They happen once, and then they're gone, leaving scientists scrambling to figure out what caused them. So, what could be behind these mysterious signals? One leading theory points to neutron stars, the dense remnants of exploded stars. Some neutron stars, known as magnetars, have incredibly strong magnetic fields. When these fields shift or snap, they could release a burst of energy powerful enough to be detected across the universe. Another possibility is that FRBs are caused by collisions between neutron stars or black holes, cataclysmic events that send shockwaves through space. But not all FRBs fit neatly into these explanations. Some repeat, sending out multiple bursts over time, while others seem to come from regions of space with no obvious sources of such extreme energy. And then there's the wild card. Could FRBs be a sign of intelligent life? It's a tantalizing idea, though most scientists are quick to point out that natural explanations are far more likely. Still, the possibility can't be entirely ruled out. After all, if an advanced civilization wanted to send a signal across the cosmos, a fast radio burst would be an efficient way to do it. But for now, FRBs remain a mystery, one that's driving astrophysicists to build more sensitive telescopes and develop new ways to detect and study these elusive signals. Why are FRBs such a big deal? Because they could be a window into entirely new cosmic phenomena. By studying them, we might learn more about the extreme environments around neutron stars, the nature of dark matter, or even the structure of the universe itself. Each burst is like a cosmic postcard carrying information from the far reaches of space. And as we decode these messages, we might uncover secrets that reshape our understanding of the cosmos. But FRBs aren't the only mysterious signals coming from the depths of space. There's another enigma, one that's just as puzzling and even more elusive. But we'll get to that next. For now, let's sit with this thought. Fast radio bursts are cosmic flashes that defy explanation, brief yet powerful enough to captivate the brightest minds on Earth. What could they be, and what might they reveal about the universe we call home? Now, let's turn our attention to one of the most tantalizing mysteries in the search for extraterrestrial life, the WOW signal. Imagine this. It's August 15, 1977. And a radio telescope in Ohio is scanning the skies for signs of intelligent life. Suddenly, a signal bursts through so strong, so unusual, that the astronomer monitoring the data circles it on the printout and writes one word next to it: WOW. This signal, lasting just 72 seconds, has become one of the most famous and debated moments in the history of the search for extraterrestrial intelligence. But what was it, and why, after more than 4 decades, does it still defy explanation? The WOW signal was unlike anything astronomers had ever seen. It was narrowband, meaning it was focused on a very specific frequency, just like the kind of signal we'd expect from an intelligent civilization trying to communicate. It was also incredibly strong, about 30 times louder than the background noise of space. And here's the kicker. It came from a region of the sky in the constellation Sagittarius, where there's no known star or planet that could have produced it. For those 72 seconds, it seemed like we might have finally found evidence of life beyond Earth. But then, just as quickly as it appeared, it vanished. And despite countless attempts to detect it again, the WOW signal has never been heard since. So, what could it have been? Some scientists argue it was a natural phenomenon, like a comet or a passing asteroid reflecting radio waves. Others suggest it might have been a glitch in the equipment or even a signal from a passing satellite. But none of these explanations fully account for the signal's unique characteristics. Its narrowband frequency, its strength, and its sudden disappearance all point to something far more intriguing. Could it have been a deliberate message from an alien civilization? It's a possibility that's hard to ignore, especially given how closely the signal matched what scientists had predicted an extraterrestrial transmission might look like. The WOW signal isn't just a cosmic curiosity, it's a reminder of how challenging the search for extraterrestrial life can be. Space is vast, and signals like this are incredibly rare. Even if they do exist, they might be fleeting, appearing and disappearing before we have a chance to study them. This is why projects like SETI, the search for extraterrestrial intelligence, continue to scan the skies, hoping to catch another glimpse of something extraordinary. But the WOW signal also raises a deeper question. If we do detect a signal from an alien civilization, how would we even know for sure? And what would it mean for humanity if we weren't alone in the universe? And speaking of the search for life beyond Earth, there's another mystery that's just as compelling, one that takes us closer to home, to the icy moons of our own solar system. But we'll get to that next. For now, let's sit with this thought. The WOW signal is a cosmic whisper, a fleeting moment that might have been our first contact with another civilization. What could it have been, and what might it mean if we ever find out? Now, let's tackle one of the most profound questions in science. If the universe is so vast with billions of stars and planets, where is everyone? This is the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where are they?" during a casual lunchtime conversation in 1950. The paradox is simple yet deeply unsettling. Given the sheer size and age of the universe, the odds of intelligent life existing elsewhere seem overwhelmingly high. So why haven't we found any evidence of it? Think about it. Our galaxy alone contains hundreds of billions of stars, many of which are orbited by planets in the so-called Goldilocks zone, where conditions are just right for liquid water and potentially life. And with billions of galaxies out there, the numbers suggest that intelligent civilization should be common. Yet, despite decades of searching, we've found nothing. No signals, no artifacts, no signs of advanced life. It's as if the universe is a vast, empty stage and we're the only actors. So, what's going on? One possible explanation is the Great Filter, a hypothetical barrier that prevents life from reaching an advanced stage. The idea is that somewhere along the path from simple organisms to spacefaring civilizations, something catastrophic happens. Maybe it's the emergence of life itself, which could be far rarer than we think. Or perhaps it's the development of intelligence, or even the ability to survive long enough to colonize the stars. If the Great Filter lies in our past, we might be incredibly lucky to have made it this far. But if it's in our future, well, that's a sobering thought. Another possibility is that intelligent life is simply rare. Maybe the conditions needed for complex life are so specific that even in a universe this big, we're one of the few, or even the only civilizations to have emerged. Or perhaps advanced civilizations are out there, but they're so different from us that we can't recognize them. They might communicate in ways we can't detect, or they might have no interest in reaching out to less advanced species like us. And then there's the darker side of the paradox. What if intelligent civilizations inevitably destroy themselves? Whether through war, environmental collapse, or some other catastrophe, it's possible that advanced societies don't last long enough to make contact. This idea ties back to the Great Filter, suggesting that the universe might be littered with the ruins of civilizations that never made it. The Fermi Paradox isn't just a thought experiment, it's a mirror that reflects our own place in the cosmos. Are we alone? Are we special? Or are we just one of many, destined to fade into silence like so many others before us? These questions are at the heart of astrobiology, the study of life in the universe, and they challenge us to think deeply about our future as a species. But while the Fermi Paradox takes us to the far reaches of the cosmos, there's another mystery much closer to home, one that might hold clues to the origins of life itself. And that's where we're headed next. For now, let's sit with this thought. The universe is vast and ancient, filled with possibilities, yet eerily silent. What does that silence mean for us, and what might we discover if we keep searching? Now, let's journey to the very edge of our solar system, to a place so distant and mysterious that it exists more in theory than in observation, the Oort Cloud. Imagine a vast spherical shell of icy objects stretching far beyond the orbit of Pluto, enveloping our solar system like a cosmic halo. This is the Oort Cloud, a hypothetical region that's thought to be the birthplace of long-period comets. those spectacular visitors that streak across our skies once every few thousand years. But here's the catch: despite its importance, we've never actually seen the Oort Cloud. So, what do we know about it, and why is it so hard to study? The Oort Cloud is named after Dutch astronomer Jan Oort, who first proposed its existence in the 1950s. He theorized that a reservoir of icy bodies must exist at the outer edges of the solar system to explain the behavior of long-period comets. These comets, like Halley's Comet, have orbits that take them far beyond the planets, sometimes taking tens of thousands of years to complete a single trip around the Sun. But where do they come from? The Oort Cloud is the leading candidate. So, what exactly is the Oort Cloud? Picture a vast collection of icy objects, comets, frozen gases, and other debris left over from the formation of the solar system. These objects are thought to be loosely bound by the Sun's gravity, orbiting at distances ranging from about 2,000 to as far as 100,000 astronomical units. To put that in perspective, 1 astronomical unit is the distance from Earth to the Sun. That means the Oort Cloud could extend nearly halfway to the nearest star. It's a mind-bogglingly vast region, and yet it's so faint and distant that we've never directly observed it. Why is the Oort Cloud so elusive? For starters, it's incredibly far away. Even our most powerful telescopes struggle to detect objects at such distances, especially when they're as small and dim as the icy bodies in the Oort Cloud. Adding to the challenge, these objects don't emit their own light, they only reflect sunlight, and at such vast distances, that light is incredibly faint. It's like trying to spot a single snowflake in a blizzard from miles away. But the Oort Cloud isn't just a cosmic curiosity, it's a time capsule from the early solar system. Studying it could reveal clues about how our planetary system formed and evolved. The icy bodies in the Oort Cloud are thought to be pristine remnants of the solar nebula, the cloud of gas and dust that gave birth to the Sun and planets. By understanding their composition, we might learn more about the conditions that led to the formation of Earth and the other planets. And then there's the role of the Oort Cloud in shaping life on Earth. Long-period comets born in this distant region have been bombarding our planet for billions of years. Some scientists believe these icy visitors may have delivered water and organic molecules to Earth, providing the building blocks for life. But they've also brought destruction. Comet impacts have shaped Earth's history, from the extinction of the dinosaurs to the formation of our oceans. So, what's next in our quest to understand the Oort Cloud? Missions like the Voyager probes are on their way to the edge of the solar system, but even they won't reach the Oort Cloud for tens of thousands of years. In the meantime, astronomers are using indirect methods to study this mysterious region, like tracking the orbits of long-period comets and searching for faint signals that might hint at its presence. But the Oort Cloud isn't the only mystery lurking in the outer solar system. Beyond its icy boundaries lies another enigma, one that's just as puzzling and even more dramatic. And that's where we're headed next. For now, let's sit with this thought. The Oort Cloud is a ghostly frontier, a place where the past and the future of our solar system collide. What secrets does it hold, and what might we discover if we could finally peer into its icy depths? Now, let's turn our gaze inward, back toward the heart of our solar system, where another mystery is quietly unfolding. For centuries, we've mapped the planets orbiting our Sun: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. But what if there's another world out there, lurking in the shadows, waiting to be discovered? This is the mystery of Planet 9, a hypothetical giant planet that could be hiding in the outer reaches of our solar system. But how do we know it's there if we've never seen it? And what would its discovery mean for our understanding of the cosmos? The story of Planet 9 begins with a strange pattern in the orbits of distant objects beyond Neptune. In the early 2010s, astronomers noticed that several icy bodies in the Kuiper Belt, a region of frozen debris left over from the solar system's formation, were behaving oddly. Their orbits were clustered in a way that suggested something massive was tugging on them, something far beyond the known planets. The gravitational influence of this unseen object seemed to be shepherding these distant worlds into peculiar, elongated paths. But what could it be? The most compelling explanation is a ninth planet, one with a mass roughly 10 times that of Earth, orbiting the Sun at a distance so vast it could take up to 20,000 years to complete a single trip around our star. So why haven't we found it yet? The answer lies in its distance and darkness. Planet 9, if it exists, would be incredibly faint, reflecting only a tiny fraction of the Sun's light. It's like trying to spot a single candle flame from the other side of a football field. To make matters worse, its orbit would be so wide and slow that pinpointing its exact location is like searching for a needle in a cosmic haystack. But astronomers aren't giving up. Using powerful telescopes and advanced computer models, they're scanning the skies, hoping to catch a glimpse of this elusive world. And the stakes couldn't be higher. Finding Planet 9 wouldn't just add another planet to our solar system, it would rewrite the story of how our cosmic neighborhood formed and evolved. But here's the real kicker. If Planet 9 exists, it raises even more questions. How did it get there? Was it born in the outer solar system, or was it flung out from the inner regions during the chaotic early days of planetary formation? And what does its presence tell us about the history of our solar system? Some scientists even speculate that Planet 9 could be a rogue planet, captured by the Sun's gravity after wandering through interstellar space. If that's true, it would mean our solar system has a cosmic hitchhiker, a world born around another star now calling our Sun its home. The search for Planet 9 is more than just a hunt for a new planet. It's a quest to understand the forces that shaped our solar system. Its discovery could shed light on the origins of distant icy worlds, the dynamics of planetary orbits, and even the possibility of other hidden planets lurking in the darkness. But for now, Planet 9 remains a tantalizing mystery, a ghostly presence at the edge of our cosmic map. And speaking of mysteries closer to home, there's another enigma waiting for us in the inner solar system, one that's just as puzzling and even more dramatic. But we'll get to that next. For now, let's sit with this thought. Planet 9 could be out there, a silent giant shaping the outer reaches of our solar system. What secrets might it hold, and what would it mean if we finally found it? Now, let's travel back in time to June 30th, 1908, to a remote corner of Siberia, where one of the most dramatic cosmic events in recorded history unfolded. It's known as the Tunguska Event, and to this day, it remains one of the most baffling mysteries in the study of our solar system. Imagine this, a massive explosion, hundreds of times more powerful than the atomic bomb dropped on Hiroshima, rips through the sky. It flattens over 2,000 square kilometers of forest, an area larger than some cities, yet leaves no crater behind. What caused this cataclysmic event? And why, more than a century later, are we still piecing together the puzzle? The Tunguska event began with a blinding flash of light, so intense it was seen hundreds of kilometers away. Witnesses reported a fireball streaking across the sky, followed by a shockwave that knocked people off their feet and shattered windows miles away. When scientists finally reached the site years later, they found a scene of utter devastation. Trees were flattened in a radial pattern, pointing away from the epicenter, as if a giant hand had pressed them down. But here's the strange part: there was no crater. No smoking gun, just a vast, eerie landscape of destruction with no obvious cause. So, what could have caused such a massive explosion without leaving a crater? The leading theory points to a cosmic intruder, a comet or asteroid entering Earth's atmosphere. But instead of hitting the ground, it exploded in mid-air, releasing an enormous amount of energy in what's known as an airburst. Think of it like a bomb detonating before it reaches the surface. The force of the explosion would have been enough to flatten forests and ignite fires, but without the telltale crater we'd expect from an impact. But here's the twist: despite decades of research, we still don't know exactly what kind of object caused the Tunguska event. Was it a rocky asteroid, an icy comet, or something else entirely? The lack of a crater has made the Tunguska event a magnet for speculation. Some scientists suggest the object might have been made of a more fragile material, like ice or loosely packed rock, which would have disintegrated completely in the atmosphere. Others propose it could have been a fragment of a larger body, breaking apart before it reached the ground. And then there are the more exotic theories, like a small black hole passing through Earth or even an alien spacecraft exploding. While these ideas are intriguing, most scientists agree that a comet or asteroid is the most likely culprit. But without physical evidence, the mystery remains unsolved. Why does the Tunguska event matter? Beyond its sheer spectacle, it's a stark reminder of the dangers posed by near-Earth objects. If an event like this happened over a populated area today, the consequences would be catastrophic. That's why the Tunguska event has become a cornerstone of planetary defense research. By studying what happened in Siberia, scientists hope to better understand how to detect and deflect potential threats from space. Missions like NASA's DART, which recently tested deflecting an asteroid, are part of this ongoing effort to protect our planet from future impacts. But the Tunguska event isn't just a cautionary tale. It's also a window into the dynamic and sometimes violent nature of our solar system. It reminds us that Earth isn't an isolated island in space, but part of a cosmic ecosystem, where asteroids and comets are constantly on the move. And while we've made great strides in tracking these objects, there's still much we don't know. What other surprises might be lurking out there, and how prepared are we for the next Tunguska? And speaking of cosmic impacts, there's another mystery tied to Earth's history, one that's just as dramatic and even more consequential. But we'll get to that next. For now, let's sit with this thought. The Tunguska event is a reminder of the power and unpredictability of the cosmos. What lessons can we learn from it? And what might it tell us about the future of our planet? Now, let's turn our attention to a mystery much closer to home, one that's been staring us in the face for billions of years. The Moon. It's our constant companion, lighting up our nights and influencing our tides. But how did it get there? The origin of the Moon is one of the most enduring puzzles in planetary science, and the answer might reveal not just how our lunar neighbor came to be, but also how Earth itself evolved into the life-sustaining world we know today. The leading theory for the Moon's formation is the giant impact hypothesis. Picture this: about 4.5 billion years ago, the early solar system was a chaotic, violent place. Planets were still forming and collisions were common. Then, one day, a Mars-sized object, sometimes called Theia, slammed into the young Earth. The impact was catastrophic, sending a massive cloud of debris into orbit around our planet. Over time, this debris coalesced, forming the Moon. It's a dramatic story, and it explains a lot, like why the Moon's composition is so similar to Earth's mantle. But here's the catch: the theory isn't perfect. For one thing, if the Moon formed from Earth's debris, why isn't its composition an exact match? The Moon has far less iron than Earth, and its oxygen isotopes are slightly different. These discrepancies have led scientists to propose tweaks to the giant impact hypothesis. Maybe Theia was made of different material, or perhaps the collision was more of a glancing blow. But even with these adjustments, some questions remain unanswered. And then there are the alternative theories. Some scientists suggest the Moon might have formed from a series of smaller impacts, each one adding to a growing pile of debris in Earth's orbit. Others propose that the Moon formed elsewhere in the solar system and was captured by Earth's gravity, though this idea struggles to explain the Moon's current orbit. There's even a wild theory that Earth once spun so fast it flung off a chunk of itself, which became the Moon. While these ideas are intriguing, none have gained as much traction as the giant impact hypothesis. So, why does the Moon's origin matter? Because it's not just about the Moon, it's about Earth. the Moon's formation was a pivotal moment in our planet's history. The impact that created it likely melted Earth's surface, reshaping its crust and atmosphere. It also gave Earth its tilt, which is crucial for our stable climate and seasons. Without the Moon, life on Earth might look very different or might not exist at all. Understanding the Moon's origin is also key to planetary science as a whole. If we can figure out how Earth and the Moon formed, we might gain insights into how other rocky planets and moons came to be. It's a puzzle that connects us to the broader story of the solar system, and one that continues to challenge and inspire scientists. But the Moon isn't the only mystery tied to Earth's cosmic history. There's another event, one that's just as dramatic and even more consequential, a moment that shaped not just our planet, but the entire course of life on Earth. And that's where we're headed next. For now, let's sit with this thought. The Moon is more than just a glowing orb in the night sky. It's a relic of Earth's violent past, a silent witness to the forces that shaped our world. What secrets might it still hold, and what might its story tell us about our place in the universe? Now, let's journey back to a time when the solar system was a chaotic, violent place, a time known as the Late Heavy Bombardment. Imagine this: around 4 billion years ago, the inner solar system was under siege. Asteroids and comets rained down on Earth, the Moon, and the other rocky planets, leaving behind scars that are still visible today. But what caused this cosmic onslaught, and how did it shape the world we live in now? The Late Heavy Bombardment is one of the most dramatic chapters in our solar system's history. For hundreds of millions of years, the inner planets were pummeled by a relentless barrage of impacts. The Moon's surface, with its countless craters, is a stark reminder of this violent era. But here's the mystery: why did this happen? The solar system had already been around for hundreds of millions of years by this point. Shouldn't things have settled down by then? One leading theory points to planetary migration. In the early solar system, the giant planets Jupiter, Saturn, Uranus, and Neptune weren't in their current orbits. Instead, they were closer together, locked in a delicate gravitational dance. But as they interacted, their orbits shifted, sending ripples through the solar system. This migration could have destabilized the asteroid belt, flinging countless rocks toward the inner planets. It's like a cosmic game of billiards, with the giant planets as the cue balls, scattering asteroids in every direction. But not everyone agrees with this explanation. Some scientists argue that the Late Heavy Bombardment might not have been a single, dramatic event, but rather a series of smaller impacts spread out over time. Others suggest that the evidence for the bombardment might be skewed by the Moon's geology, which preserves craters far better than Earth's constantly changing surface. So, why does this matter? Because the Late Heavy Bombardment wasn't just a destructive force, it was also a creative one. The impacts brought water and organic molecules to Earth, ingredients that may have been crucial for the emergence of life. Some scientists even think that the bombardment could have kick-started the chemical reactions that led to the first living organisms. But it also raises a haunting question: could such an event happen again? The Late Heavy Bombardment is a reminder of how dynamic and unpredictable the solar system can be. It shaped Earth's early environment, setting the stage for life to emerge. But it's also a mystery that continues to challenge our understanding of planetary formation and evolution. And speaking of life, the Late Heavy Bombardment takes us to the edge of another profound question: where did life come from? This brings us to our next mystery, one that's just as puzzling and even more consequential. But we'll get to that next. For now, let's sit with this thought. The Late Heavy Bombardment was a cosmic storm that reshaped the solar system. What secrets does it hold about our origins, and what might it tell us about the potential for life elsewhere in the universe? Now, let's dive into a mystery that blurs the line between astronomy and biology, a theory that suggests life on Earth might not have started here at all. What if the seeds of life were delivered to our planet from the depths of space? This is the idea behind Panspermia, a theory that proposes life on Earth originated from microorganisms hitchhiking on comets, asteroids, or even cosmic dust. But how plausible is this idea, and what evidence do we have to support it? The concept of panspermia isn't new. In fact, it dates back to ancient Greece, where philosophers speculated that life could travel through the cosmos. But in modern science, panspermia has gained traction thanks to discoveries that suggest life might be more resilient and more widespread than we once thought. For example, we've found microorganisms that can survive in extreme environments, from the scorching heat of hydrothermal vents to the freezing vacuum of space. Some bacteria, like Deinococcus radiodurans, can even withstand intense radiation, making them potential candidates for interstellar hitchhikers. But how could life survive a journey through space? One possibility is that microorganisms could be shielded inside comets or asteroids, protected from radiation and extreme temperatures. When these objects collide with a planet, they could deliver their microbial passengers, seeding life in a new environment. This idea gained support in the 1980s when scientists discovered organic molecules, the building blocks of life, in meteorites. One famous example is the Murchison meteorite, which fell in Australia in 1969. It contained amino acids, the same molecules that make up proteins in living organisms. Could these molecules have been the precursors to life on Earth? The case for panspermia got even stronger in 2015, when the European Space Agency's Rosetta mission discovered complex organic molecules on comet 67P. This finding suggested that comets could carry the ingredients for life across the solar system. But here's the catch: while we've found evidence that life's building blocks can survive in space, we haven't yet found definitive proof that living organisms can make the journey. So what are the challenges to panspermia? For one, the journey through space is incredibly harsh. Even if microorganisms could survive the cold and radiation, they'd still have to endure the intense heat and pressure of entering a planet's atmosphere. And then there's the question of timing. For panspermia to work, life would have to arise somewhere else in the universe and then travel to Earth, all within the relatively short window of time when our planet was forming and becoming habitable. Despite these challenges, panspermia remains a compelling idea, not just for explaining the origins of life on Earth, but for the search for life elsewhere in the universe. If life can travel between planets, it means the cosmos could be teeming with it. This theory bridges the gap between astronomy and biology, suggesting that the story of life might be written not just on Earth but across the stars. And speaking of the building blocks of life, there's another mystery that takes us even deeper into the origins of life itself, one that's just as fascinating and even more fundamental. But we'll get to that next. For now, let's sit with this thought. If life on Earth came from space, what does that mean for our place in the universe? And what might we discover if we keep looking beyond our planet? Now, let's dive into one of the most profound mysteries of all. How did life begin? It's a question that has puzzled scientists for centuries, and while we've made incredible strides in understanding the building blocks of life, the full picture remains elusive. One of the most compelling theories is the RNA World Hypothesis, a bold idea that suggests life on Earth might have started with a molecule called RNA. But what is RNA, and why is it so central to this mystery? And if this hypothesis is true, what does it mean for the search for life beyond Earth? RNA, or ribonucleic acid, is often called the cousin of DNA. Like DNA, it can store genetic information, but it's also capable of something extraordinary. It can act as an enzyme, speeding up chemical reactions. This dual role makes RNA a prime candidate for the first molecule of life. The RNA World Hypothesis proposes that before DNA and proteins existed, RNA was the star of the show, a molecule that could both store information and catalyze the reactions needed to build more complex structures. It's like a Swiss Army knife of biochemistry, capable of doing it all. But how could RNA have formed in the first place? Scientists think the early Earth was a chemical playground with simple molecules like water, ammonia, and methane interacting under the influence of heat, lightning, and ultraviolet light. Over time, these interactions could have produced the building blocks of RNA nucleotides, and once RNA molecules formed, they might have started replicating, creating the first self-replicating systems. From there, it's a short leap to the emergence of life as we know it. The RNA World Hypothesis has some strong evidence to back it up. For example, RNA is still central to life today. It plays a key role in translating genetic information into proteins, and some viruses use RNA as their genetic material instead of DNA, but the hypothesis isn't without its challenges. One major hurdle is the complexity of RNA itself. Forming RNA from scratch in a lab is incredibly difficult, and scientists still don't fully understand how it could have happened naturally on the early Earth. Another challenge is the question of where RNA came from. Did it form spontaneously, or was there some kind of catalyst that helped it along? Some scientists think minerals or clay surfaces might have played a role, providing a template for RNA molecules to assemble. Others suggest that RNA might not have been the first molecule of life at all. Perhaps simpler molecules paved the way, with RNA emerging later. Despite these questions, the RNA World Hypothesis remains one of the most promising ideas for explaining the origin of life. And it's not just about Earth, it has profound implications for astrobiology, the search for life beyond our planet. If RNA or something like it is the key to life's beginnings, then planets with similar chemical conditions might also be capable of giving rise to life. This idea drives missions to places like Mars and Europa, where scientists are searching for signs of past or present life. But the RNA World Hypothesis also raises a deeper question. What are the fundamental rules of chemistry that make life possible? This takes us into the realm of another mystery, one that's just as fascinating and even more fundamental, but we'll get to that next. For now, let's sit with this thought. If RNA was the spark that ignited life on Earth, what does that mean for the universe? Could the same spark be waiting to light up other worlds? And what might we discover if we keep searching for the chemistry of life? Now, let's shift our focus to a cosmic mystery that's pulling galaxies and our curiosity toward it. Imagine a force so powerful that it's tugging entire galaxies, including our own Milky Way, through the vast expanse of space. This is the Great Attractor, a mysterious gravitational anomaly that's been baffling scientists for decades. But what exactly is it, and why is it so hard to study? The story of the Great Attractor begins in the 1970s when astronomers noticed something strange. Galaxies in our local universe, including the Milky Way, were all moving in the same direction. It was as if an invisible hand was pulling them toward a single point in space. This point, located about 250 million light-years away, became known as the Great Attractor. But here's the catch. It lies in a region of the sky called the Zone of Avoidance, an area obscured by the dense dust and stars of our own galaxy. It's like trying to see a lighthouse through a thick fog, nearly impossible. So, what makes the Great Attractor so powerful? The leading theory is that it's a massive concentration of matter, perhaps a supercluster of galaxies whose gravity is strong enough to influence the motion of galaxies across vast distances. But even this explanation raises more questions. Why is there such a dense cluster of matter in this particular spot? And what role does it play in the larger structure of the universe? To understand the Great Attractor's significance, we need to zoom out and look at the universe on a grand scale. The cosmos isn't just a random scattering of galaxies, it's a vast web of filaments and voids, with galaxies clustered along the threads like beads on a string. The Great Attractor seems to sit at a key intersection in this cosmic web, acting as a gravitational anchor that shapes the flow of galaxies around it. But its exact nature remains elusive, hidden behind the veil of the Zone of Avoidance. Despite the challenges, astronomers are making progress. Using infrared and radio telescopes, which can peer through the dust of the Milky Way, scientists have begun to map the region around the Great Attractor. What they've found is even more intriguing. The Great Attractor itself might be part of an even larger structure, known as the Laniakea supercluster. This colossal network of galaxies spans over 500 million light-years, with the Great Attractor at its heart. It's a reminder that the universe is far more interconnected than we once thought. But the Great Attractor isn't just a cosmic curiosity, it's a window into the forces that shape the universe on the largest scales. By studying it, we might learn more about dark matter, the invisible substance that makes up most of the universe's mass, and dark energy, the mysterious force driving the universe's expansion. It's a puzzle that connects the local universe to the cosmos as a whole, challenging us to rethink our place in the grand scheme of things. And speaking of cosmic structures, the Great Attractor takes us into the realm of another mystery, one that's just as puzzling and even more dramatic. But we'll get to that next. For now, let's sit with this thought. The Great Attractor is a gravitational enigma, a force that's pulling galaxies and our understanding of the universe into uncharted territory. What secrets might it hold, and what might we discover if we could finally see beyond the zone of avoidance? Now, let's zoom out even further, way beyond individual galaxies or clusters, and take in the universe on its grandest scale. Imagine a tapestry woven from threads of dark matter and gas, stretching across billions of light-years, connecting galaxies like beads on an invisible string. This is the cosmic web, a vast network of filaments that forms the backbone of the universe. But what exactly are these cosmic filaments, and why do they hold the key to understanding how galaxies, and perhaps even life itself, came to be? Cosmic filaments are the largest structures in the universe, massive threads of dark matter and gas that weave through the cosmos, linking galaxies and galaxy clusters in an intricate web. They're like the scaffolding of the universe, shaping its structure on the grandest scales. But here's the catch. While we can map their presence through their gravitational effects, we've never directly observed them. They're made up of dark matter, which doesn't emit light, and diffuse gas that's incredibly faint. So how do we even know they're there? The answer lies in the way galaxies move. Just as the Great Attractor pulls galaxies toward it, cosmic filaments exert a gravitational influence, guiding the flow of galaxies across the universe. By studying the distribution and motion of galaxies, scientists have been able to trace the outlines of these filaments, revealing a web-like structure that spans the cosmos. But despite this progress, cosmic filaments remain one of the most poorly understood features of the universe. So, why are they so important? Because they're not just cosmic decorations, they're the highways along which galaxies form and evolve. Think of them as rivers of gas flowing through the universe and feeding the growth of galaxies. When two filaments intersect, they create dense knots of matter where galaxies and galaxy clusters are born. Without these filaments, the universe might be a much emptier, darker place. But cosmic filaments also raise profound questions. For one, how do they form in the first place? The leading theory ties them to the early universe, when tiny fluctuations in density imprinted during the Big Bang grew over billions of years, pulled together by gravity into the vast web we see today. It's a story that connects the universe's birth to its present-day structure, but it's still full of gaps. For example, how do the filaments interact with dark energy, the mysterious force driving the universe's expansion? And what role do they play in the distribution of dark matter, the invisible substance that makes up most of the universe's mass? These questions aren't just academic, they're central to our understanding of the cosmos. By studying cosmic filaments, scientists hope to unlock the secrets of galaxy formation, dark matter, and even the fate of the universe itself. Missions like the European Space Agency's Euclid telescope are designed to map the cosmic web in unprecedented detail, shedding light on these elusive structures and their role in the universe's evolution. But the cosmic web isn't just a scientific puzzle, it's also a reminder of how interconnected the universe truly is. Every galaxy, every star, every planet is part of this vast network, shaped by forces that stretch across billions of light years. It's a humbling thought, and one that raises even more questions about the nature of the cosmos. And speaking of the universe's largest structures, there's another mystery waiting for us, one that's just as mind-bending and even more dramatic. But we'll get to that next. For now, let's sit with this thought. Cosmic filaments are the threads that bind the universe together, shaping its past, present, and future. What secrets might they hold, and what might we discover as we continue to unravel the cosmic web? Now, let's stretch our imaginations beyond the boundaries of our universe and into the realm of the multiverse. What if our universe isn't the only one? What if there are countless others, each with its own laws of physics, its own stars, planets, and maybe even its own versions of us? This is the mind-bending idea of the multiverse, a concept that's as controversial as it is captivating. But is it science or science fiction? And what would it mean if we discovered that our universe is just one of many? The multiverse isn't a single idea but a collection of theories, each proposing a different way that multiple universes could exist. One of the most prominent is eternal inflation, a theory that suggests our universe is just one bubble in a vast cosmic foam. Imagine the Big Bang not as a one-time event, but as a never-ending process with new universes constantly bubbling into existence, each with its own unique properties. Some might have stronger gravity, others might have no stars at all, and a few might even have life forms we can't even imagine. Then there's string theory, which takes the multiverse idea even further. String theory proposes that the fundamental building blocks of the universe aren't particles but tiny, vibrating strings. These strings exist in higher dimensions, up to 10 or 11, depending on the version of the theory. And our universe is just one slice of this multidimensional reality. In this view, the multiverse isn't just a collection of universes but an infinite landscape of possibilities, where every conceivable version of reality exists somewhere. But here's the catch: the multiverse is, by its very nature, speculative, because these other universes, if they exist, are beyond our ability to observe or interact with. They're incredibly hard to test. Some scientists argue that this makes the multiverse more of a philosophical idea than a scientific one. After all, if we can't prove it, does it really belong in the realm of science? Despite these challenges, the multiverse has profound implications for both physics and philosophy. For physicists, it could solve some of the biggest mysteries in cosmology, like why the constants of nature, things like the speed of light or the strength of gravity, seem so finely tuned for life. If there are infinite universes, each with different constants, it's not surprising that at least one would have the right conditions for life to exist. For philosophers, the multiverse raises questions about our place in reality. Are we just one version of ourselves in an infinite sea of possibilities? And what does that mean for free will, identity, and the nature of existence? The multiverse is a reminder that the universe, or universes, are far stranger and more complex than we can imagine. It challenges us to think beyond the limits of our own reality and consider the possibility that there's more out there than we'll ever know. And speaking of the nature of reality, the multiverse takes us into the realm of another mystery, one that's just as mind-bending and even more fundamental. But we'll get to that next. For now, let's sit with this thought. If the multiverse is real, what does that mean for our understanding of existence? And what might we discover if we could peer beyond the edges of our own universe? Now, let's turn our attention to one of the most fundamental mysteries of all, one that shapes every moment of our lives yet remains deeply enigmatic: the nature of time. What is time, really? Why does it flow in one direction, carrying us from the past to the future, when the laws of physics seem to work just as well in reverse? And could time itself hold the key to understanding the universe's ultimate fate? At first glance, time seems simple. It's the ticking of a clock, the rising and setting of the sun, the aging of our bodies. But when we dig deeper, time becomes far more elusive. In physics, time is treated as a dimension, much like space. Yet, unlike space, time has a direction, an arrow that points from the past to the future. This is known as the arrow of time, and it's one of the most puzzling features of our universe. So, why does time have a direction? The answer lies in a concept called entropy, which measures the amount of disorder in a system. According to the second law of thermodynamics, entropy always increases over time. Think of it like this: if you drop a glass, it shatters into pieces, but those pieces will never spontaneously reassemble into a glass. This increase in entropy gives time its arrow, creating a clear distinction between past and future. But here's the catch: while entropy explains why time flows in one direction, it doesn't explain why the universe started with such low entropy in the first place. This brings us to the Big Bang. At the moment of the universe's birth, entropy was incredibly low, setting the stage for the arrow of time we experience today. But why was the early universe so ordered? Some scientists think the answer lies in the multiverse, where our universe is just one of many, each with its own initial conditions. Others suggest that time itself might be an emergent property, arising from more fundamental processes we don't yet understand. Then there's the block universe theory, which challenges our everyday experience of time. According to this idea, past, present, and future all exist simultaneously, like frames in a film. In this view, time doesn't flow, it just is. The passage of time is an illusion, a trick of our perception. It's a radical idea, but one that aligns with Einstein's theory of relativity, which treats time as a dimension woven into the fabric of space-time. So, what does all this mean for our understanding of the universe? Time isn't just a backdrop for events, it's a dynamic, mysterious force that shapes the cosmos. It connects the Big Bang to the present, and it may hold clues to the universe's ultimate fate. Will time continue to flow forever, or will it come to an end in a cosmic freeze or a fiery collapse? These are questions that keep physicists up at night, and they remind us that time is more than just a measure of moments. It's a window into the deepest mysteries of existence. And as we reflect on these 20 mind-bending space mysteries, from dark matter to the nature of time, one thing becomes clear: the universe is far stranger and more wondrous than we can imagine. Each mystery challenges us to think bigger, to question what we know, and to keep searching for answers. Because in the end, it's not just about solving puzzles, it's about understanding our place in the cosmos and the incredible story of how we came to be. So, what do you think? Which of these mysteries fascinates you the most? And what questions about the universe keep you up at night? Let's keep exploring, keep wondering, and keep reaching for the stars. Because the universe is full of secrets, and the journey to uncover them is just beginning. As we come to the end of our journey through these 20 mind-bending space mysteries, one thing is clear: the universe is a place of endless wonder and profound questions. From the invisible grip of dark matter to the explosive power of fast radio bursts, from the haunting silence of the Fermi Paradox to the cosmic dance of the Great Attractor, each mystery challenges our understanding of reality and pushes the boundaries of human knowledge. These aren't just puzzles for scientists, they're invitations for all of us to look up at the night sky and wonder. What makes these mysteries so captivating isn't just their complexity, but what they represent: the relentless human drive to explore, to question, and to understand. Every unanswered question is a spark that ignites curiosity, driving us to build better telescopes, design more ambitious missions, and dream bigger dreams. These mysteries remind us that science isn't just about finding answers, it's about asking the right questions and embracing the unknown. Think about it: every time we uncover a piece of the cosmic puzzle, it leads to even more questions. Dark matter and dark energy make up 95% of the universe, yet we still don't know what they are. The origins of supermassive black holes and the nature of time itself remain shrouded in mystery. And the search for extraterrestrial life, it's only just beginning. These aren't just scientific challenges, they're stories waiting to be told, discoveries waiting to be made. So what's next? The future of space exploration is brighter than ever. Missions like the James Webb Space Telescope are peering deeper into the cosmos than ever before, while projects like the Event Horizon Telescope are giving us our first glimpses of black holes. Meanwhile, scientists are working tirelessly to unravel the secrets of dark matter, decode the origins of life, and even test the boundaries of the multiverse. The answers are out there, and every breakthrough brings us one step closer to understanding the universe and our place within it. But here's the thing, you don't have to be a scientist to be part of this journey. Every time you look up at the stars, every time you share a fascinating fact with a friend, every time you wonder about the mysteries of the cosmos, you're joining in the greatest adventure of all, the quest to understand the universe. So, what do you think? Which of these mysteries fascinates you the most? Are you captivated by the eerie silence of the Fermi Paradox, or do you find yourself drawn to the explosive power of fast radio bursts? Maybe you're intrigued by the idea of the multiverse or the enigmatic nature of time itself. Whatever it is, let's keep the conversation going. Share your thoughts in the comments below, and let's explore these cosmic wonders together. And if you've enjoyed this journey through the universe's greatest mysteries, don't forget to hit that like button, share this video with your fellow space enthusiasts, and subscribe for more cosmic explorations. The universe is full of secrets, and the adventure is just beginning. Thanks for watching, and remember, the stars are waiting. Let's keep reaching for them.